Our universe might be just one page in an infinite cosmic library. This is the Multiverse Hypothesis, and it is moving from science fiction into serious scientific debate. By the end of this exploration, you will understand 30 distinct reasons why leading physicists now believe multiple universes could be real. We will examine how the bizarre rules of quantum mechanics and the vast echoes of the Big Bang itself point toward a reality far grander than we ever imagined. What does it mean for our place in existence if everything that can happen does happen somewhere? That first instant of existence holds the key to our entire cosmic story. To understand the first compelling reason scientists entertain the multiverse, we must look back to a fraction of a second after the Big Bang, to a concept called cosmic inflation. Proposed by physicist Alan Guth, this idea suggests our universe didn't just expand, it underwent a breathtaking exponential growth spurt, stretching from a subatomic speck to something cosmically vast in less than a blink. This solves profound mysteries, like why the universe looks so uniform in all directions and why its geometry appears flat. But here is where the plot thickens. The mathematics of inflation suggests something remarkable. Once this inflationary process begins, it may not have a clean stop. Instead, it could be eternal. Think of a pot of water boiling endlessly. In most of the pot, inflation continues at a frantic pace, but here and there, bubbles form. In each of these bubbles, inflation stops, and a stable universe like our own crystallizes out of that frenzied expansion. Each bubble is entirely separate, sealed off from the others, potentially with its own unique set of physical constants and laws. Our entire observable cosmos, with all its hundreds of billions of galaxies, could be just one such bubble in an infinite, frothing sea of ongoing creation. This isn't a fringe idea. It's a direct consequence of the leading theory that explains our universe's very existence. Scientists like Andrei Linde developed this into the model of eternal chaotic inflation, where the multiverse isn't an accident but an inevitable outcome. The mechanism that gave birth to our smooth and structured reality inherently manufactures a landscape of others, making our universe not a singular event, but a single leaf on an endlessly growing tree. But a bubble universe is just the beginning of the story. What makes our particular bubble so special? The answer lies in the numbers that define reality itself. The universe runs on a set of fundamental constants, precise numerical values that never change. The strength of gravity, the charge of an electron, the force that holds atomic nuclei together, each is fixed at a specific, delicate value. And here is the staggering mystery. If any one of these numbers were altered by even a minuscule fraction, the universe as we know it would vanish. A slightly stronger gravitational constant, and stars would burn out in a cosmic flash, leaving no time for planets to form. A slightly weaker nuclear force, and hydrogen would never fuse into helium, meaning no stars would ignite at all. The universe would be a dark, empty expanse of scattered particles. This isn't a matter of opinion, it's a result of rigorous calculation. The conditions for complex structures, let alone life, exist within an impossibly narrow window of these constants. It appears the cosmos has been fine-tuned with breathtaking precision. For many scientists, this fine-tuning problem is one of the deepest puzzles in all of physics. Why does our universe have this seemingly perfect, life-permitting recipe? One profound answer emerges from the multiverse concept. If there are countless other universes, each with its own random set of physical constants, then every possible combination of numbers gets tried out somewhere. In the vast majority of these universes, the numbers don't add up. They are stillborn, empty, or chaotic. But by the sheer law of large numbers, a few will, by pure chance, land on the winning lottery ticket, the precise combination that allows for galaxies, stars, planets, and observers. We are not in a special universe, we are simply in a habitable one. Our existence is the selection bias. This idea is known as the Anthropic Principle. It states that any valid theory of the universe must account for the fact that we are here to observe it. The multiverse transforms an agonizing mystery of perfect design into a statistical inevitability. It suggests we are not the purpose of creation, but rather a fortunate accident in a cosmic landscape of infinite variety. The fine-tuning of our universe points to a landscape of possibilities, but what about the decisions happening right now? Quantum mechanics, the rulebook for the smallest particles, presents a paradox that directly suggests a multiverse. Take the classic thought experiment of Schrödinger's cat. In its sealed box, a quantum event decides the fate of the animal, meaning according to the textbook Copernican interpretation, the cat exists in a blurry state of being both alive and dead until someone looks inside. This idea that reality requires a conscious observer to snap into focus has troubled physicists for decades. In the 1950s, a graduate student named Hugh Everett offered a breathtakingly elegant alternative. He suggested the math does not require a collapse. Instead, every single possible outcome of a quantum event actually occurs. When the moment of measurement happens, our single universe doesn't choose a path. It splits like a branching road, creating entirely separate, real worlds for each possibility. In one branch, the observer finds a living cat. In the newly formed branch right beside it, another version of that same observer finds a cat that has passed. Both outcomes are equally real, just forever separated. This is the many worlds interpretation. Its power lies in its simplicity. It takes the equations of quantum mechanics at face value without adding the extra, mysterious rule about observation. Leading physicists like David Deutsch champion this view, arguing it is the most straightforward reading of the laws that govern atoms and particles. The implication is staggering. Every time a particle could go left or right, every quantum fluctuation, every seemingly random event doesn't just represent a probability. It represents a fork in the road of reality. A near-infinite tree of branching universes is constantly growing from the fabric of existence itself, generated by every quantum event everywhere. This reason for the multiverse isn't about cosmic beginnings or fine-tuning. It is woven into the fundamental, everyday workings of reality, suggesting that with every passing moment, countless other versions of our world are quietly coming into being, each following a different thread of possibility. Yet another layer of the cosmos opens up when we ask what reality is made of at its most fundamental level. For decades, physicists have sought a single, elegant framework to unite the vast scale of gravity with the tiny quantum world, a theory of everything. The leading candidate is string theory. It proposes a breathtakingly beautiful idea. The universe's most basic ingredients are not point-like particles, but unimaginably tiny, vibrating loops of energy, strings. The different notes or harmonics of these vibrating strings would manifest as all the particles and forces we see, from electrons to photons to gravity itself. It is a symphony written into the fabric of space and time, but this beautiful theory comes with a profound and unexpected consequence. The mathematics of string theory do not yield one unique solution, one perfect set of cosmic laws. Instead, they allow for a number of possible configurations so vast it defies human comprehension, perhaps 10 to the power of 500 different solutions. That is a 1 followed by 500 zeros, a number greater than all the atoms in our observable universe. Each solution represents a self-consistent set of physical laws, a complete cosmic rulebook. This is what physicists call the landscape of string theory. Our universe, with its specific strength of gravity and charge of an electron, is just one single point in this unimaginably vast cosmic terrain. The landscape is not a metaphor for different places, but for different sets of fundamental physics. to make sense of why we find ourselves in this particular point on the landscape, with its life-permitting rules, the multiverse idea becomes almost necessary. If the landscape of possibilities is real, then the only way to realize even a fraction of them is if multiple universes actually exist, each crystallizing with a different set of laws from the string theory catalog. Physicist Leonard Susskind powerfully argues this point. For string theory to describe our reality, it must naturally generate a multiverse, a cosmic arena where every possible set of laws gets its chance to play out. In most of these universes, the physics would be sterile, incapable of forming complex structures. But in a rare few, like our own, the vibration of the strings would align in just the right way to allow for stars, planets, and the emergence of life. This reason ties the grand cosmic scales of inflation to the tiniest vibrations of reality itself, suggesting that the multiverse may be woven into the deepest mathematical fabric of existence. The light from the dawn of time carries a secret message. 13.8 billion years after the Big Bang, we can still detect its faint afterglow, a nearly uniform bath of microwave radiation that fills every corner of the sky. This cosmic microwave background is our most detailed baby picture of the universe, a snapshot from when it was just 380,000 years old. For decades, it was seen as the ultimate proof of a smooth, homogeneous beginning, a canvas of near-perfect uniformity. But when satellites like Planck mapped this ancient light with exquisite precision, they found something deeply puzzling. The map is not perfectly smooth. Scattered across the sky are strange, large-scale anomalies, regions that are inexplicably cooler than they should be, or align in peculiar ways that seem to defy the standard model of cosmology. One area, whimsically nicknamed the cold spot, is a vast circular region of space significantly chillier than its surroundings. According to our best theories, such a feature is statistically almost impossible to have formed by random chance alone. So what could have left these cosmic bruises on the fabric of our infant universe? A compelling and controversial hypothesis points directly to the multiverse. Cosmologist Laura Mersini-Horton has proposed that these anomalies could be imprints from a colossal event in our distant past, a collision with another bubble universe during the early, frothing stages of eternal inflation. Think of two soap bubbles gently bumping into one another as they float in a sink. The point of contact leaves a subtle deformation on each bubble's surface. In the same way, if our expanding bubble universe brushed against a neighboring one in that frenzied primordial foam, the immense energy of that interaction could have left a permanent scar, a region of space with a slightly different temperature and density, frozen into the cosmic microwave background for all time. This transforms ancient light from a simple historical record into a potential window. If these anomalies are indeed signatures of other universes, then we are not just theorizing about the multiverse. We may be looking at its direct archaeological evidence, a fossilized imprint of a neighboring reality on our own sky. While this interpretation remains hotly debated, it offers something extraordinary, a testable, observational pathway to potentially confirm we are not alone in the cosmic foam. But perhaps the strangest clues for a multiverse come from the darkest objects in the cosmos. Black holes present a paradox so deep it threatens to unravel our understanding of reality itself. According to quantum mechanics, information can never be truly destroyed. Every particle carries data about its history, and that data must be preserved even if transformed. Yet, according to general relativity, anything that crosses a black hole's event horizon is lost forever, its information seemingly erased from our universe. This is the black hole information paradox, a fundamental conflict between our two most successful theories of physics. For decades, it seemed one law of nature must break. The solution, however, may be even more extraordinary. It comes from an idea called the holographic principle, championed by physicist Leonard Susskind. This principle suggests a radical notion. All the information that describes everything within a three-dimensional volume of space, every star, every planet, every person, is not stored within that volume at all. Instead, it is perfectly encoded on the two-dimensional boundary that surrounds it, like a cosmic barcode etched onto the surface of a sphere. Think of a credit card hologram. The flat, shiny sticker contains all the data needed to project a three-dimensional image. In the same way, our rich, three-dimensional reality, with all its depth and movement, could be a magnificent projection from a two-dimensional surface at the edge of the universe. This isn't just philosophy. The mathematics of black holes strongly supports it, suggesting the information swallowed by a black hole isn't lost inside, but is smeared across its event horizon, preserved forever on its surface. Now extend this breathtaking logic one step further. If our entire universe can be described as a holographic projection from its outer boundary, what projects that boundary? Some interpretations of the holographic principle open a door to an even grander architecture. Our universe could be one holographic surface among many, each projecting its own internal reality, all existing within a higher dimensional multiverse. In this view, solving the paradox of what happens to information in a black hole doesn't just save quantum mechanics. It provides a potential blueprint for a cosmos of multiple, coexisting holographic realities, each a complete and self-contained projection, like different movies playing on separate screens hanging in a vast, higher dimensional theater. The quest to preserve a fundamental rule of physics leads us to a vision where our tangible world is a magnificent illusion, a cosmic shadow play cast from the edge of something far greater. The holographic universe suggests our reality is a projection, but what if it is something even more fundamental? Physicist Max Tegmark pushes the logic of the multiverse to its ultimate conclusion with what he calls the mathematical universe hypothesis. He proposes a breathtakingly simple yet profound idea. Our universe is not merely described by mathematics, as a planet's orbit is described by an equation. Instead, our universe is a mathematical structure. Think of a circle. The perfect, abstract concept of a circle exists independently, with its own set of properties and relationships. Tegmark argues that physical existence and mathematical existence are one and the same. If a mathematical structure is logically consistent, free from internal contradictions, then it exists as a physical reality somewhere. In this view, the universe you are experiencing right now is not made of matter and energy in a void. It is a vast, self-consistent pattern of mathematical relationships, and we are complex patterns within that pattern, perceiving it from the inside. This leads to what Tegmark terms a level 4 multiverse, the final and most expansive tier. It encompasses every single mathematical structure that can possibly exist. Every variation of physical laws, every conceivable geometry of space-time, every possible arrangement of particles and forces that can be described by a consistent set of equations is out there as a real physical universe. Our cosmos, with its specific laws of physics, is just one entry in an infinite, abstract library of all logical possibilities. This reason is not based on a new observation from a telescope or an experiment in a particle collider. It is a philosophical argument rooted in the nature of mathematics itself. If we accept that the world is fundamentally mathematical, and that mathematics describes all that is possible, then the existence of a multiverse becomes not just likely, but logically inevitable. It pushes the idea of reality to its most extreme edge, suggesting that everything that can be simply is. The very act of looking at the world may be what breaks it. This is the profound and unsettling puzzle at the heart of quantum mechanics known as the measurement problem. In the standard textbook version, a particle like an electron does not have a definite position or state until it is observed. Before measurement, it exists as a blurry cloud of possibilities, a mathematical entity called a wave function that describes all the places it could be. But the instant a scientist sets up a detector to look, that spread-out wave function mysteriously collapses, and the electron snaps into one specific, concrete location. The question that has haunted physicists for nearly a century is simple. What exactly constitutes an observation? Is it a conscious mind, a machine? And what physical process triggers this sudden, irreversible change from potential to actual? This rule of collapse feels like a strange, arbitrary addition to the otherwise elegant equations of quantum theory. It introduces a fundamental split between the quantum realm, governed by probabilities, and the classical world of definite objects, without a clear boundary between them. It is as if the universe has two sets of rules, and we do not know where the switch gets flipped. The desire to remove this philosophical thorn, to have one single, seamless set of laws describing all of reality, drives one of the strongest arguments for the multiverse. The many worlds interpretation offers a breathtakingly simple solution. It states the wave function never collapses at all. The mathematics, taken completely seriously, shows it simply continues to evolve smoothly and deterministically. So what happens when we make a measurement? The universe does not choose one outcome. It splits or branches so that every single possibility described by the wave function becomes real in a newly formed parallel world. In one branch, the detector clicks and registers the electron here. In another, equally real branch, a different version of that same experiment records the electron there. There is no magical collapse because every possible result physically occurs. This transforms quantum mechanics from a theory about probabilities and sudden jumps into a theory about the continuous, branching structure of reality itself. It provides a cleaner, more complete foundation, where the equations describe everything without needing an extra, unexplained rule about observation. For many physicists, this elegant resolution is not just convenient. It is a powerful sign that we are on the right track, that the multiverse may be the price we pay for a universe that operates by a single, consistent, and beautiful set of laws from the smallest particle to the vastness of cosmic structure. Einstein famously called it spooky action at a distance, a phenomenon so bizarre it seemed to break the universe. Quantum entanglement occurs when two particles become linked, their fates intertwined no matter how far apart they travel. Measure one particle here on Earth and its partner, perhaps on the other side of the galaxy, instantly snaps into a corresponding state. This connection happens faster than light, defying our classical understanding of space and locality. It suggests a layer of reality where separation is an illusion, where everything is profoundly interconnected. This non-locality, this eerie togetherness across vast distances, is a cornerstone of quantum mechanics, yet it remains deeply mysterious. Why should the universe operate this way? One radical answer emerges from the multiverse concept, a theory known as many interacting worlds proposed by physicists like Howard Weissman, offers a stunning reinterpretation. It suggests that what we perceive as the weird probabilities of a single quantum world are actually the result of countless, nearly identical parallel worlds constantly interacting with one another. In this view, every particle exists in many worlds at once, but these worlds are not completely isolated. They exert a subtle, repulsive force on their immediate neighbors in the vast landscape of realities. When we perform an entanglement experiment, we are not seeing magic. We are witnessing the outcome of this gentle push and pull between an immense stack of parallel worlds, each containing a slightly different version of the particles. The instantaneous correlation across space is not a signal traveling faster than light. It is a global pattern emerging from the collective behavior of all these interacting realities. The spooky action becomes a natural consequence of a deeper architecture. While this idea is speculative, it demonstrates the explanatory power of the multiverse framework. It takes one of the most puzzling features of our reality, a feature that seems to violate common sense, and provides a potential mechanism that makes it feel almost ordinary. Entanglement stops being a paradox and starts looking like a clue, a faint signal of the subtle conversations happening between our world and its nearest neighbors in an infinite ensemble. It hints that the boundaries between realities may be more porous than we think, woven together by the same fundamental fabric that creates the illusion of separation in the first place. The very tools we use to understand our universe can become windows into others. This leads us to a powerful and often misunderstood concept, the Anthropic Principle, and its surprising ability to predict the nature of reality. Often dismissed as a mere philosophical tautology, the idea that we observe a universe compatible with our existence has been wielded as a precise scientific instrument. Its most stunning success came in predicting one of the greatest cosmic mysteries of our time, dark energy. In the late 1990s, two teams of astronomers made a Nobel Prize-winning discovery. They found that the expansion of the universe is not slowing down as everyone expected, but is actually accelerating. Something was pushing galaxies apart with ever-increasing speed. This something was dubbed dark energy, and its strength is represented by a number called the cosmological constant. The shock was not just that this constant existed, but its value. It is positive but incredibly, almost impossibly tiny. If it were just a little bit larger, the repulsive force would have been so strong in the early universe that it would have ripped apart every proton and atom before they could ever form stars or planets. If it were slightly more negative, acting like an attractive force, the universe would have collapsed back in on itself in a fraction of a second. Our cosmos exists on a razor's edge. For years, physicists struggled to explain why this number is so small, yet not zero. It seemed like a bizarre and arbitrary accident of nature. This is where the Anthropic Principle, combined with the multiverse, offered a profound answer. Theorists like Steven Weinberg explored the idea in the late 1980s. They reasoned that if a multiverse exists, with countless bubble universes, each having a randomly assigned value for the cosmological constant, then most of those universes would have values too large or too small for any interesting structure to form. They would be empty or short-lived, but in a tiny, tiny fraction of these bubbles, by pure statistical chance, the constant would land within the narrow, habitable window. Observers, by definition, could only arise in those rare, life-permitting bubbles. Therefore, if we find ourselves in a universe with a small, non-zero cosmological constant, it is not a miracle. It is a selection effect. The stunning part is that Weinberg used this reasoning to actually calculate the range of values we should expect to measure. He predicted that the cosmological constant, when finally discovered, would be small but not zero, and within an order of magnitude of what we could potentially observe. Years later, when the accelerating universe was measured, the value fell almost perfectly within his predicted range. This was not a post hoc explanation. It was a genuine, if probabilistic, prediction that came true. The multiverse framework, through the lens of the Anthropic Principle, turned an inexplicable fine-tuning from a baffling puzzle into a predictable outcome of a larger cosmic landscape. It showed that this idea is not just philosophical speculation, but a tool that can make testable statements about our world, lending indirect but powerful support to the notion that our universe is one of many. But what if the boundaries of our reality are not just mathematical but physical? The 11th reason emerges from a breathtaking extension of string theory called Brane cosmology. This concept provides one of the most vivid and tangible pictures of the multiverse imaginable. The word brane is short for membrane. In this framework, our entire three-dimensional universe, with all its galaxies and stars, is not floating in nothingness. It is a vast three-dimensional sheet, a brane, suspended within a higher dimensional space called the bulk. Think of our universe as a single, impossibly large page of an infinite book. Each page is flat and two-dimensional from its own perspective, yet they are all stacked together in the three-dimensional volume of the book itself. In Brane cosmology, we are the page, and the bulk is the space between the pages, a realm with extra spatial dimensions that our senses are utterly blind to. This idea transforms the multiverse from an abstract collection of bubbles into a geometric architecture, other branes, representing other complete universes with their own laws of physics, could be floating parallel to ours in this higher dimensional bulk, separated by a gap we cannot cross or even perceive. They are right next to us in a direction we cannot point. This leads to a staggering possibility. If these branes are moving within the bulk, they could occasionally collide. The titanic energy released in such a collision could be the very spark that ignites a Big Bang. Physicists like Paul Steinhardt have explored models where our universe's hot, dense beginning was not a singular point of creation from nothing, but the aftermath of a colossal impact between our brane and a neighboring one. In this view, the Big Bang was not the beginning of everything, but a local event in a much older, multidimensional cosmos. Brane cosmology offers a powerful spatial metaphor. It suggests separate realities are not infinitely far away in some abstract landscape, but could be physically adjacent, layered like sheets of paper in a cosmic ream, vibrating and moving in a grand, higher dimensional dance. The reason we do not see them is simply because we are trapped on our own sheet, unable to look sideways into the bulk. This framework makes the multiverse feel concrete, a place not just of different laws, but of actual, albeit inaccessible, geography. The idea that we are living inside a computer simulation may sound like the plot of a science fiction film, but it is taken seriously by a growing number of philosophers and technologists. This simulated universe hypothesis, while often discussed on its own, shares a profound and unexpected kinship with the scientific arguments for a multiverse. The logic was laid out by philosopher Nick Bostrom in a now famous thought experiment. He reasoned that if a civilization ever reaches a level of technological maturity capable of creating vast, detailed simulations of conscious beings, then the number of simulated minds would quickly come to vastly outnumber the minds in the original, base reality. Think of a video game developer creating an open world. One developer can spawn millions of detailed, interactive characters, each believing their digital city is the only world that exists. Now scale that up to a civilization with cosmic computing power. They could run not one, but billions of such simulations, each with its own unique history and physical laws. This creates a staggering statistical likelihood. If such simulations are possible anywhere in the cosmos, then for every single base reality, there could be trillions upon trillions of simulated ones. Therefore, if you are a conscious being wondering about your origins, the numbers are overwhelmingly against you being in the original, physical universe. You are far more likely to be one of the simulated minds. This argument mirrors the anthropic reasoning we see in the multiverse. Just as we are more likely to find ourselves in one of the many life-permitting bubble universes rather than a rare, perfectly tuned singular one, we are more likely to find ourselves in one of the many common simulated realities rather than the singular, original base reality. The simulation hypothesis essentially proposes a technological multiverse, a vast stack of artificial worlds generated by advanced intelligence. From our limited perspective inside the system, we could never tell the difference. The laws of physics we study would simply be the underlying code of the simulation, and any glitches or oddities in quantum mechanics or cosmic constants could be seen as rounding errors or legacy code in a grand program. While this idea pushes the boundaries of science into philosophy, it adds a compelling layer to the multiverse conversation. It suggests that the proliferation of realities might not only be a natural feature of cosmology or quantum mechanics, but could also be a deliberate act of creation, an endless branching tree of worlds crafted not by cosmic inflation, but by intelligence. Whether our universe is a natural bubble in an inflationary foam or a line of code in a cosmic computer, the conclusion points in the same direction. We are almost certainly not alone in the grand scheme of existence. The story of our cosmos is written in competing theories, each a masterpiece of logic and observation. Yet they all seem to converge on a single, startling conclusion. Consider the fate of the universe. The standard model tells us it began in a fiery Big Bang and will end in a cold, dark, eternal expansion. But other brilliant minds have proposed radically different destinies, and these alternatives often require us to think in cycles, not in a single, linear story. Take the idea of a cyclic universe, a cosmos that breathes. In some models, the universe expands from a Big Bang, reaches a maximum size, and then contracts back down in a big crunch, only to rebound in a new Big Bang over and over for eternity. Each cycle could have slightly different physical constants, a slightly different arrangement of matter. From the perspective of any beings within one cycle, their universe has a definite beginning and end. But from the outside, it is just one link in an endless chain. Each cycle is in every meaningful sense a separate universe, born from the ashes of its predecessor and destined to give birth to its successor. They exist in sequence, not in parallel, but they still form a multiverse across time. Then there is the breathtaking vision of physicist Roger Penrose, called Conformal Cyclic Cosmology. He suggests that as our universe expands toward an unimaginably distant future, all matter will eventually decay into radiation, and the distinction between time and space will blur away. At this point of infinite smoothness, the end of our universe becomes mathematically identical to the beginning of another. Our cosmic eon, as he calls it, gives rise to a new one in an infinite series. The remnants of black holes from our universe might even leave faint imprints, called Hawking points, on the next eon's cosmic microwave background. In this view, universes are not isolated bubbles, but successive chapters in an eternal book, each with its own Big Bang, yet forever connected to what came before. Even bouncing cosmologies, where our universe emerges from the collapse of a previous one via quantum processes, point to a reality beyond our single epoch. The persistence of these diverse and serious models is telling. They are not fringe ideas. They are attempts by our greatest thinkers to solve the deepest puzzles of existence, from the initial singularity to the ultimate fate of all things. And time and again, the mathematics does not lead to a solitary, one-off event. It leads to repetition, it leads to cycles, it leads to sequences. The concept of a multiverse, in one form or another, emerges not as a wild speculation, but as a recurring, almost inevitable theme in our quest to understand where we came from and where we are going. It seems the universe, in its deepest nature, resists being alone. This ancient drive to understand reality's fullness whispers through centuries of human thought. Long before telescopes or particle colliders, philosophers like Plato and Aristotle wrestled with a profound idea, the principle of plenitude. They reasoned that a truly complete and perfect creation would not leave possibilities unfulfilled. If something can exist in the grand scheme of things, it should exist. All genuine potential must find its expression in the tapestry of reality. This is not a scientific argument in the modern sense, but a deep philosophical intuition about the nature of existence itself. It suggests a cosmos that holds back, that only creates one specific version of things when countless others are possible, would feel strangely incomplete, even wasteful. It would raise a more troubling question: why this one and not the others? What makes our particular arrangement so special as to deserve being the sole reality? Modern cosmology has breathed startling new life into this ancient thought. We now know the laws of physics, as we understand them, do not dictate a single, inevitable universe. Quantum mechanics offers a landscape of probabilities. The mathematics of inflation and string theory suggest a vast landscape of possible cosmic outcomes, each with different constants, forces, and even dimensions. The Principle of Plenitude takes this scientific insight and pushes it to its logical conclusion. If the fundamental rules allow for different kinds of universes, then a truly full, abundant, and non-arbitrary reality would contain them all. The multiverse, in this view, is the ultimate embodiment of cosmic generosity. It is a reality that refuses to waste a single possibility. Our universe, with its specific fine-tuned parameters, is not a lonely, special miracle. It is simply one flowering branch on an endlessly fertile tree of existence. This transforms our perspective from one of cosmic solitude to one of cosmic belonging. We are not a fragile, singular accident in a void. We are a necessary expression of a reality so rich and fertile that it brings forth everything that can be. The philosophical hunger for a universe without arbitrary boundaries finds a powerful answer in the scientific image of an infinite multiverse, suggesting that existence in its deepest nature is inherently abundant. The second law of thermodynamics is one of the most reliable rules in all of science. It tells us that disorder, or entropy, always increases over time. A shattered glass does not spontaneously reassemble. A hot cup of coffee left on a table cools down to room temperature, its energy dispersing, never to gather back into the cup. The universe itself is on an irreversible slide from order to chaos, a one-way street toward a featureless, lukewarm end known as heat death. Yet this ironclad law presents us with a profound and often overlooked mystery. If entropy only increases, then the universe must have started in a state of incredibly low entropy, a condition of exquisite, improbable order. Think of finding a pristine, unshuffled deck of cards in a casino. Every card is in perfect numerical and suit sequence. That is our cosmic starting point. This is called the past hypothesis, and it is one of the deepest puzzles in physics. Why did the universe begin in such a special, ordered state? Why wasn't it born in a state of maximum chaos, which would have made the formation of stars, planets, and life utterly impossible? The sheer improbability of our low entropy beginning is staggering, far more extreme than the fine-tuning of physical constants. Some physicists, like Sean Carroll, argue that explaining this initial condition is perhaps the most important unsolved problem in cosmology. The multiverse offers a powerful and elegant solution. If we consider proposals for how a universe can quantum mechanically arise from nothing or bounce from a previous state, these processes do not typically produce one single, perfectly ordered cosmos. They would naturally generate a vast ensemble of universes, each with its own random set of initial conditions. In the overwhelming majority of these baby universes, entropy would be high from the very first moment. They would be stillborn soups of maximum disorder, expanding into formless voids where no structure could ever coalesce. But in an exceptionally rare subset, by pure statistical chance, the starting entropy would be low. These would be the decks of cards that came out of the box perfectly ordered. In those rare universes, the second law would kick in, providing the necessary arrow of time and driving the complex processes that lead to galaxies, chemistry, and life. We find ourselves in one of those rare, ordered beginnings not because it was designed for us, but because we could not possibly find ourselves anywhere else. A high-entropy universe has no observers to wonder about its origin. This transforms the past hypothesis from a baffling miracle into a predictable selection effect within a much larger multiverse. It suggests that the very arrow of time, the feeling that the past is fixed and the future is open, is not a fundamental feature of reality but a local condition of our particular cosmic bubble, a gift from an inconceivably vast lottery of beginnings. Our cosmic horizon is a prison of light and time. From our vantage point on Earth, we can peer out across the vastness, capturing photons that have journeyed for over 13 billion years to reach our telescopes. This defines our observable universe, a magnificent but finite sphere centered on us. Yet this sphere has a hard boundary, not a physical wall, but a limit set by the speed of light itself. Because the universe has a finite age, light from regions beyond a certain distance simply has not had time to reach us yet. Those realms are forever hidden, locked outside our cosmic event horizon. But what lies in those unreachable depths? The standard assumption is that they are more of the same, an endless continuation of galaxies and cosmic web stretching into infinity. However, the theory of eternal inflation suggests something far more radical. If the inflationary process that birthed our bubble never truly stopped everywhere, then the distant, unobservable cosmos may not be a uniform extension of our local neighborhood. Instead, as we look farther out, we might eventually cross into regions where inflation is still ongoing, or where it stopped under different conditions, giving rise to bubble universes with entirely different physical laws. What we call the unobservable universe might not be a single entity at all, but a frothing sea of disconnected realities. This transforms a simple limitation of observation into a profound philosophical point. Our entire scientific endeavor is built upon what we can see and measure. But if the true nature of total reality includes vast domains that are forever inaccessible to us, domains that may be as different from our universe as a star is from a stone, then labeling all of this as one universe starts to feel inadequate. The word universe, from the Latin for turning toward one, implies a single, unified whole. But if the whole is fundamentally fractured, with regions causally severed from one another and operating under different rules, the multiverse becomes the more honest and accurate term. It acknowledges that our observable patch, for all its grandeur, is just a single room in an infinite mansion, and we can never receive a postcard from the other wings. The limit of our sight may not be a barrier to knowledge, but a clue pointing to a reality of unimaginable diversity lying just beyond the edge of every telescope. Theories earn their credibility not from being beautiful, but from being right. Among the most triumphant predictions in modern cosmology is the detailed portrait of the cosmic microwave background radiation. Before its precise measurement, the infant universe was a realm of pure speculation. The theory of cosmic inflation made a series of bold, testable forecasts. It said the CMB should be almost perfectly uniform because the rapid stretching would have ironed out any primordial wrinkles. It predicted the exact spectrum of tiny temperature fluctuations, the specific statistical signature of quantum seeds stretched to cosmic size. It foretold that the geometry of the universe should be flat. When satellites like COBE, WMAP, and finally Planck mapped the sky, the data returned a verdict. The predictions matched the observations with breathtaking precision. Inflation was not just a clever idea, it was a framework that told us what to look for, and the universe obliged. This predictive success is the gold standard of science, but like any powerful theory, inflation comes with implications that extend beyond the original questions it was designed to answer. The simplest and most elegant versions of inflationary theory, the ones that so perfectly match our data, do not naturally produce a single, tidy universe and then stop. Their mathematics tend to run away with themselves, leading inevitably to the scenario of eternal inflation, a process that spawns bubble universes without end. This creates a fascinating chain of reasoning for scientists to follow. We have a theory that works spectacularly well to explain our observable cosmos. That same theory, when its equations are followed to their logical conclusion, suggests our universe is one of many. Do we accept the theory for its successful predictions but reject its most natural consequence? Many physicists argue that to do so would be arbitrary, like accepting that gravity makes an apple fall from a tree, but refusing to believe it also holds the moon in orbit around the Earth. The success of inflation forms a sturdy foundation. We trust this foundation because it supports the entire edifice of our modern understanding of the cosmos. If that foundation also has a basement we did not initially notice, a basement containing doors to other rooms, it is not scientific to ignore it simply because we cannot yet walk through those doors. The predictive track record forces us to take the multiverse implication seriously, not as a certainty, but as a compelling and direct extension of our best explanation for how everything began. The search for a single theory of everything inevitably leads us back to the multiverse. This is the quantum gravity conundrum. For over a century, physics has been split between two magnificent but incompatible rulebooks. Quantum mechanics governs the bizarre, probabilistic world of atoms and particles with stunning accuracy. General relativity describes the graceful curvature of spacetime by stars and galaxies with equal perfection. Yet when these two theories meet at the center of a black hole or the first instant of the Big Bang, the math breaks down into nonsense. Unifying them into a single framework of quantum gravity is perhaps the greatest challenge in all of science. And intriguingly, the leading candidates for this unified theory do not point toward a solitary cosmos. They point toward a plurality. Take loop quantum gravity, an approach that suggests spacetime itself is not smooth and continuous, but woven from tiny, finite loops, a fabric of interwoven threads. When this idea is applied to cosmology, it offers a breathtaking possibility. Instead of a singular Big Bang emerging from nothing, the equations suggest a big bounce. Our expanding universe could be the rebound from a previous cosmic phase that contracted down to an incredibly dense state, only to spring back into a new expansion. This implies a cyclical sequence, a chain of universes across time, each a chapter in an eternal story. Similarly, other frameworks like causal set theory, which views reality as a vast network of discrete events, naturally generate a rich tapestry of possible spacetime structures. The key insight is this: when physicists try to stitch the fabric of reality together at its most fundamental level, the solutions they find are rarely singular. The mathematics of quantum gravity resist producing one unique, inevitable universe. Instead, they tend to describe a landscape of possibilities, a spectrum of ways for spacetime to be. The multiverse, in this light, is not an add-on or a speculative extra. It emerges as a common, almost unavoidable feature in our most serious attempts to heal the deepest fracture in our understanding of nature. If the ultimate laws of physics are to be complete and consistent, they seem to require a stage far larger than the single universe we call home. The cosmos is not merely expanding, it is fleeing from itself at an ever-increasing pace. This discovery, which earned a Nobel Prize, was not just surprising, it was a profound shock that rewrote the destiny of everything. For decades, astronomers assumed the mutual gravitational pull of all the galaxies would gradually slow the universe's expansion, like a ball tossed upward slowing as it climbs. The great debate was whether that slowdown would eventually reverse into a catastrophic big crunch or simply coast toward a frozen halt. Then, in the late 1990s, two independent teams measuring distant supernova delivered an answer that defied all expectation. The expansion is not slowing down at all, it is accelerating. Some mysterious, repulsive force, now called dark energy, is pushing galaxies apart harder and harder as time goes on. This was a monumental puzzle. What could this force be? The simplest candidate is the cosmological constant, a kind of innate energy woven into the fabric of empty space itself. But its measured value created an even deeper mystery. It is positive, meaning it pushes, but it is almost unbelievably tiny. If it were just a little bit larger, the repulsive force in the early universe would have been so powerful it would have blown apart every proton, atom, and star before they could ever form. No galaxies, no planets, no life. If it were slightly more negative, acting like an attractive force, the cosmos would have collapsed back on itself in a fraction of a second. Our universe exists on a knife edge of improbability. Why is this number so perfectly poised to allow for our existence? This is where the multiverse framework transforms a baffling coincidence into a predictable outcome. In a landscape of countless bubble universes, each born with a randomly assigned value for dark energy, the vast majority get it wrong. Most bubbles have far too much dark energy, inflating into empty, featureless voids before any structure can take hold. Others have too little or a negative value, collapsing instantly or never allowing matter to clump into galaxies. But in a vanishingly small fraction of these bubbles, by pure statistical chance, the dark energy value lands within the narrow, habitable window. It is weak enough to allow galaxies to form over billions of years, yet strong enough to drive the accelerating expansion we now observe. We, of course, find ourselves in one of those rare, life-permitting bubbles. This is not a design, it is a selection effect. The stunning part is that this anthropic reasoning was used to make a genuine prediction. Years before dark energy was discovered, physicist Steven Weinberg calculated that if a multiverse existed, observers would most likely measure a cosmological constant that was small but not zero, within an order of magnitude of what might someday be detected. When the accelerating universe was finally measured, the value landed almost perfectly within his predicted range. The peculiar, delicate amount of dark energy that fills our cosmos, one of the greatest observational mysteries of our time, fits the multiverse prediction like a key in a lock. It suggests that what we once saw as a bizarre accident of our solitary universe may instead be a telling signature of our address in a much grander cosmic neighborhood. A single, perfectly tuned universe stands as a profound question mark in the mind of science. Why this particular set of laws? Why these exact numbers? If our cosmos is truly all that exists, then its specific configuration becomes what philosophers call a brute fact, an ultimate given with no deeper reason or cause. It simply is, for the scientific spirit which thrives on tracing chains of causality and finding underlying principles, this can feel deeply unsatisfying. It is the equivalent of hitting a wall in an investigation, a final answer of just because. The multiverse hypothesis offers a powerful way through that wall. It reframes our universe's specific fine-tuning not as a random, inexplicable miracle, but as a statistical necessity within a much larger ensemble. In a cosmos of countless universes, every possible set of physical constants gets its chance. The parameters of our reality are no longer arbitrary. They are selected from a vast distribution, like drawing a single ticket from a cosmic lottery. This does not completely eliminate the mystery, of course. It shifts the fundamental question from why this universe to why this multiverse with these particular rules for generating universes. Yet for many thinkers, this is a profound step forward. It replaces a single, staggering coincidence with a structured, generative framework. It reduces the number of unexplained, one-off facts about existence. The multiverse, in this view, is not an extravagant addition to reality. It is an economy of explanation, a way to satisfy our deep metaphysical desire for a complete and coherent story. The drive to find theories that leave no loose ends, that feel necessary rather than accidental, is a powerful engine behind scientific progress. When faced with the alternative, a solitary cosmos that seems suspiciously and inexplicably arranged for life, the the multiverse emerges as the more comprehensive, and for some, the more elegant answer. It transforms our universe from a lonely, special case into a natural, even expected, occurrence within a grander causal tapestry. The strange power of a quantum computer lies in its ability to hold multiple answers at once. Unlike a classical computer bit, which is definitively a 1 or a 0, a quantum bit or qubit can exist in a superposition, a blend of both states simultaneously. This allows it to explore many computational pathways in parallel, promising to solve problems that would take conventional machines longer than the age of the universe. But this magical superposition is incredibly fragile. The moment a qubit interacts with its surrounding environment, be it a stray photon or a vibration, it seems to collapse into a single, definite state. This process is called decoherence, and it is the greatest engineering challenge in building a practical quantum computer. From one perspective, decoherence is the enemy, a loss of precious quantum information that turns a powerful superposition into a mundane classical result. But from the vantage point of the many worlds interpretation, decoherence is not a loss at all. It is the mechanism of creation. When a qubit in superposition interacts with its environment, that interaction doesn't erase the other possibilities. Instead, it entangles the qubit with every particle it touches. The different states of the qubit become correlated with different states of the entire surrounding world. In one branch of reality, the environment records one outcome of the calculation. In a newly formed, equally real branch, a different version of that same environment records the other outcome. The information is never destroyed. It is simply distributed across the branching structure of the multiverse. For some theorists working at the bleeding edge of quantum information science, this view is more than philosophy. It provides a profound clarity. It frames the universe itself as a vast, ongoing quantum computation, where every interaction is a step in a cosmic algorithm that continuously generates new branches of reality. The practical struggle to build a quantum computer to protect qubits from decoherence becomes a direct confrontation with the architecture of existence. The fact that this many worlds perspective offers such a clean, logical explanation for the core process of quantum information processing is, for its proponents, a powerful form of evidence. It suggests that the most advanced technology humans are building may be giving us a glimpse into the fundamental, multi-branched nature of reality itself. Our place in the cosmos has never been as central as we once believed. Look back through the history of astronomy, and you will find a recurring theme of profound humility. For centuries, the Earth was seen as the unmoving center of all creation, with the stars and planets revolving around us in perfect celestial spheres. Then came Copernicus, who dared to suggest the sun was the center, and our world was just another planet in motion. This was the first great cosmic demotion. Later, we learned our sun is not the center of the galaxy, but a rather ordinary star in its distant suburbs. Then, in the early 20th century, Edwin Hubble revealed that our Milky Way is just one island universe among countless others, scattered across a vast and growing sea of space. Each of these revelations dismantled a layer of our assumed specialness. We are not at the center of the solar system, the galaxy, or the universe. This pattern is undeniable. It shows that whenever we have clung to the idea that we occupy a unique or privileged position, the universe has gently but firmly corrected us. The proposal of a multiverse fits perfectly within this historical arc. It suggests the next and perhaps ultimate step in this journey of cosmic humility. Our entire universe, with its hundreds of billions of galaxies, may not be the totality of existence. It could be one among an infinite number of other realities, each with its own history and laws. To resist this idea simply because it makes our cosmos feel less special is to ignore the clear lesson written across centuries of discovery. Our intuition about being at the center, about being singular, has been wrong every single time. Philosophically, it would be inconsistent to assume the pattern stops here. The multiverse is not a wild leap into speculation. It is the logical continuation of a trend that has defined our growing understanding of reality for over 500 years. It asks us to embrace a final, breathtaking demotion, not of our planet or our star, but of our entire cosmic home, placing it within a grander, more populous architecture of existence than we ever dreamed possible. The most common criticism leveled at the multiverse is also its most important scientific test. Skeptics argue that if other universes are forever beyond our reach, the idea is untestable and therefore not real science but mere philosophy. Yet this challenge has sparked a wave of remarkable creativity among theorists. They are not content to simply speculate. They are actively designing potential experiments, hunting for the faint, indirect signatures that a multiverse might leave on our own reality. This pursuit transforms the concept from an abstract possibility into a legitimate scientific hypothesis, one that could, in principle, be confirmed or refuted by evidence. One promising avenue looks back to the cosmic microwave background, that ancient snapshot of the infant universe. If our cosmos began as a bubble in an eternally inflating foam, it's possible, though not guaranteed, that it collided with a neighboring bubble in that primordial chaos. Such a titanic event would have sent shockwaves through the fabric of our young universe, leaving a distinct circular pattern of temperature variations imprinted on the CMB. Astronomers have already scanned the data from the Planck satellite, searching for these cosmic bruises. While no definitive collision signature has been found yet, the very fact that scientists know what to look for and have actively looked is significant. It means the hypothesis makes a specific, falsifiable prediction about our observable sky. Another approach considers the landscape of string theory. If the fundamental constants of nature can vary across different universes, could there be a mechanism that allows a trace of that variation to leak into our own? Some models suggest that if other branes or bubbles interact very weakly with ours, they might impose subtle shifts on the values we measure, shifts that could someday be detected in ultra-precise particle physics experiments. Perhaps the most direct test lies in the realm of quantum gravity. If the many worlds interpretation is correct and reality constantly branches, there might be minuscule, calculable effects on how quantum systems evolve that differ from other interpretations. Researchers at institutions like the Perimeter Institute for Theoretical Physics are working to devise tabletop experiments sensitive enough to detect these differences, seeking the fingerprints of branching in the lab. The active, ongoing pursuit of these tests is what matters most. It demonstrates that leading physicists are not treating the multiverse as a finished story or an article of faith. They are treating it as a work in progress, a framework that suggests where to point our telescopes and how to design our next generation of experiments. The possibility of being proven wrong is not a weakness of the idea. It is its greatest strength, elevating the multiverse from untestable philosophy into the rigorous, evidence-driven arena of modern cosmology. Separate paths through the forest of physics are all leading to the same clearing. This is the 24th reason to consider the multiverse real, the remarkable convergence of independent lines of thought. It is not just one field of science hinting at this radical possibility. The idea emerges compellingly from at least 4 distinct and powerful branches of modern physics, each working on its own fundamental puzzles. From cosmology, the theory of eternal inflation gives us a cosmos frothing with bubble universes. From quantum mechanics, the many worlds interpretation shows reality perpetually branching with every decision. From string theory, we get a vast landscape of possible physical laws, a cosmic catalog awaiting realization. And from the foundations of mathematics, the mathematical universe hypothesis suggests every consistent structure is a real physical place. These are not minor variations on a theme. They are profound frameworks developed by different communities of scientists using different tools to solve completely different problems. The cosmologist worries about the smoothness of the early universe. The quantum physicist grapples with the paradox of measurement. The string theorist seeks to unify all forces. The mathematician probes the nature of reality itself. Yet, when each follows the logic of their own discipline as far as it can go, they all seem to arrive at a similar, breathtaking vista, a reality far larger than a single universe. This convergence carries immense weight in science. It is akin to multiple witnesses standing at different corners of an intersection, all independently describing the same accident. Their stories may differ in detail, perspective, and emphasis, but the core event they report is identical. If only one person claimed to see it, we might be skeptical. But when four separate, reliable observers who have never spoken to each other tell you the same extraordinary story, you start to believe something truly happened. This interdisciplinary reinforcement transforms the multiverse from a speculative idea born in one corner of physics into a robust, cross-checked hypothesis. It suggests we are not chasing a phantom, but triangulating on a deeper truth about the architecture of existence. The fact that such different paths of inquiry, each with its own evidence and internal consistency, all point toward a pluralistic cosmos, makes the idea far more compelling and difficult to dismiss. It indicates the multiverse may be less of a speculative add-on and more of an unavoidable implication woven into the very fabric of our best descriptions of reality. Probability itself becomes a different kind of puzzle in a solitary universe. What does it really mean to say a quantum particle has a 50% chance of spinning up or down before we look? Is chance a fundamental property of reality, or just a measure of our ignorance? This question has troubled physicists since the dawn of quantum theory, because in a single cosmos, probability feels like a ghost in the machine, a mathematical tool without a clear physical anchor. The many worlds interpretation offers a startlingly concrete answer. In a branching multiverse, probability is not about something that might happen. It is about something that does happen and how often it happens across the vast tree of reality. Think of a coin toss in our world. We say it has a 50% chance of landing heads. In a single universe, only one outcome occurs, and the probability is a prediction of which one. But in the many worlds view, both outcomes occur with absolute certainty, each in its own newly formed branch. The 50% probability is not a prediction of an event, but a measure of existence. It tells you what fraction of the total number of observer moments, or conscious experiences, will find themselves in the branch with heads versus the branch with tails. It becomes a counting problem across an ensemble of real worlds. For a physicist seeking to remove any trace of subjectivity or mystery from the laws of nature, this is a profoundly attractive resolution. It grounds the fuzzy concept of chance in something tangible, the architecture of branching realities. Probability is no longer a statement about what will be, but a census of what already is across the multiverse. This reinterpretation provides a cleaner, more objective foundation for quantum theory itself, suggesting that the mathematics of probability we use to predict the behavior of atoms is actually a map of the distribution of experiences across the infinite and ever-dividing tree of existence. The silence of the cosmos is one of its most profound mysteries. For decades, the Fermi paradox has echoed through our search for meaning among the stars. If the universe is so vast and old with billions of potentially habitable planets, why do we see no signs of other civilizations? Where is everybody? This haunting question may find its most elegant resolution not within our single universe, but outside of it, within the architecture of a multiverse. In a solitary cosmos, the absence of other intelligent life feels like a glaring anomaly, a puzzle that demands an answer. But if our universe is just one among a near-infinite ensemble, the paradox transforms. The conditions for the rise of a technological civilization might be astronomically rare, requiring a perfect alignment of cosmic constants, planetary stability, and evolutionary chance. In the vast statistical distribution of universes, most would be sterile, incapable of fostering any life at all. A smaller fraction might allow for simple organisms. An even tinier sliver could give rise to intelligence, and within that sliver, only a microscopic subset might see that intelligence survive long enough to broadcast its presence across the galaxy. We may simply reside in one of those exceptionally rare universes where, by a roll of the cosmic dice, we are alone in our galactic neighborhood, or perhaps among the very first to awaken. Alternatively, the answer could be even more expansive. Perhaps advanced civilizations are common in other universes with more favorable laws of physics, but they are forever separated from us by the ultimate barrier, the boundary between realities. Their signals, their artifacts, their grandest engineering projects are all confined to their own cosmic bubble, leaving our sky silent. The multiverse does not solve the Fermi paradox with a single answer. Instead, it reframes the entire question. It expands the canvas of possibility, moving the paradox from a troubling problem specific to our lonely universe to an expected feature of a broader cosmic distribution. The eerie quiet we hear when we listen to the stars may not be a sign of our solitude, but a signature of our address, a clue that we inhabit one particular room in an infinite mansion where the conditions for conversation are exceptionally, and perhaps blessedly, rare. A scientific puzzle can be a dead end, or it can be a signpost pointing toward a new frontier. The multiverse hypothesis serves precisely this second role, acting as a powerful guiding principle for the entire field of fundamental physics. When researchers confront the seemingly arbitrary numbers that govern our cosmos, the traditional question has been, why these exact values? This line of inquiry, pursued within a single universe framework, has often led to frustration. The constants appear fine-tuned, yet no deeper mechanism within our known laws explains their precise, life-permitting numbers. It is as if you found a perfectly crafted key on the ground and spent years trying to understand why the key itself is shaped that way, rather than looking for the lock it was designed to fit. The multiverse perspective reframes the entire investigation. It shifts the focus from a why question to a how question. Instead of asking why the constants are what they are, physicists are now guided to ask, what kind of process could generate a wide distribution of different constants across a landscape of possibilities? This is a fundamentally different and far more productive line of scientific thinking. It directs theorists to build models that naturally produce diversity. String theory's landscape is a prime example. Rather than being seen as a flaw because it predicts too many possible universes, this vastness becomes the central feature, the very mechanism for generating the variety that the multiverse concept requires. Similarly, models of eternal inflation are studied not just for how they create our smooth universe, but for how they naturally spawn a frothing sea of bubbles, each with potentially different physical properties. This guiding principle has opened entirely new avenues of research. Scientists are now exploring how transitions between different vacuum states could occur, how constants might vary across a brane in higher dimensional space, or what the statistical distribution of life-permitting universes might look like within an infinite ensemble. These are concrete, mathematical questions that can be explored with rigor. By accepting the multiverse as a plausible framework, physics avoids the intellectual dead end of simply labeling our universe's features as miraculous brute facts. It provides a roadmap, a heuristic that says, if the answer isn't here, look for a larger structure that could contain it. This practical utility, this ability to generate fruitful new questions and prevent science from stalling, is a compelling reason for its serious consideration. It transforms the multiverse from a speculative conclusion into an invaluable tool for discovery, lighting the path forward through the deepest mysteries of existence. The human hunger for other worlds is ancient and undeniable. Long before the first telescope peered into the void, our myths and stories were filled with hidden realms and parallel existences. From the spirit worlds of indigenous traditions to the layered heavens and underworlds of classical epics, from the many worlds of Hindu cosmology to the fairy rings and magical portals of European folklore, we have always sensed that our reality might not be the only one. This deep cultural and narrative resonance is not scientific proof, but it is a powerful form of human evidence. It tells us that the multiverse idea touches something fundamental in the human psyche, a persistent intuition that our single, linear experience of life is not the full story. When modern science began to whisper about bubble universes and branching realities, it did not land on deaf ears. It landed in minds already prepared by millennia of storytelling to find the concept not just plausible, but profoundly meaningful. This cultural preparedness is invaluable. It makes an extraordinarily complex scientific hypothesis feel intuitively explorable, transforming it from an abstract equation into a landscape the public imagination can willingly enter. This engagement has a very real, practical effect on the progress of science itself. Widespread fascination fuels public interest, which in turn supports funding for ambitious research in cosmology and fundamental physics. It inspires new generations of thinkers not just in laboratories, but in philosophy departments and artist studios, creating a rich ecosystem where ideas can cross-pollinate. A novelist's take on branching time might spark a new line of inquiry for a physicist. A filmmaker's visual metaphor for higher dimensions might help a professor explain string theory to a classroom. This vibrant dialogue between human imagination and empirical inquiry creates the intellectual environment where such radical science can be seriously pursued, debated, and refined. It shows that our drive to tell stories about the cosmos and our drive to understand its mechanics are not separate endeavors. They are twin engines of discovery, one fueling the other in a continuous loop of wonder and investigation. The fact that our oldest stories and our newest science seem to be converging on the same breathtaking vista suggests we may finally be developing the language, both mathematical and metaphorical, to describe a truth we have felt in our bones for thousands of years. Time may be the most familiar and mysterious dimension of our existence. We feel it flowing from past to future, an irreversible current that carries us from memory into anticipation. Yet modern physics paints a startlingly different portrait. Einstein's theory of relativity fused time with space into a single, four-dimensional fabric, where the distinction between past, present, and future is not absolute, but depends on one's perspective and motion. This leads to the block universe view, where all of history, from the Big Bang to the distant future, exists eternally as a fixed structure. Every moment is already there, like frames in a cosmic film reel. We simply experience it frame by frame. Quantum mechanics adds another layer of strangeness, with its probabilities and potentialities that seem to resolve only when observed. The multiverse, particularly when combined with the many worlds interpretation, offers a breathtaking synthesis of these puzzling ideas. Imagine the block universe not as a single, linear film, but as an immense, branching library of films. Every possible outcome of every quantum event spawns a new reel, a new timeline. In this grand, static multiverse block, every moment of every possible history exists eternally. The flow of time, the feeling that the future is open and the past is fixed, becomes a local illusion, a story told within each individual branch. We are conscious beings moving along one thread of this vast, frozen tapestry, mistaking our journey along the thread for a river that creates the landscape. This perspective elegantly resolves profound puzzles about time's arrow. Why does disorder always increase? Why do we remember the past but not the future? In the multiverse block, the increase of entropy and the direction of our experience are built into the geometry of the branching structure itself. Our conscious awareness is like a train on one track in an infinite rail yard, always moving forward along a branch where cause precedes effect. This provides a coherent, if deeply humbling, picture of reality. Your childhood, this present moment, and every possible future version of you all exist with equal solidity in an unchanging, multidimensional sculpture. The multiverse becomes the ultimate home for our fractured understanding of time, offering a framework where the subjective flow of experience and the objective frozenness of space-time can finally coexist without contradiction. It suggests that to understand time, we must look beyond the confines of our single universe to the timeless architecture that contains all possible versions of it. The journey of discovery has been a long retreat from the center. We have moved our home from the heart of creation to a rocky planet orbiting an ordinary star in a quiet suburb of a spiral galaxy, itself lost in a sea of countless others. Each step taught us the same humbling lesson that we are not special, not central, not unique. This relentless pattern, known as the Copernican Principle, is more than just a historical footnote. It is a guiding philosophy of modern science, a rule of thumb that has proven astonishingly reliable. Whenever we have been tempted to believe our vantage point is privileged, the universe has shown us otherwise. To stop this progression now at the very edge of the cosmic horizon and declare that our entire universe, with all its hundreds of billions of galaxies, is the one and only reality, would be to break faith with this profound and successful tradition. It would be an act of ultimate cosmic arrogance, placing our entire cosmic domain on a pedestal from which we have spent centuries removing everything else. The multiverse hypothesis is the final, logical step in this grand revolution. It applies the Copernican principle not just to our planet or our galaxy, but to the totality of existence as we know it. It asserts that our universe, for all its splendor, is not a singular miracle. It is a typical member of a vast, perhaps infinite, ensemble. In a multiverse, our specific set of physical laws and cosmic constants is not a one-off masterpiece. It is simply one possible configuration among a near infinity of others, some barren, some bizarre, and a precious few capable of giving rise to conscious beings like us. This philosophical commitment to non-specialness provides a powerful, overarching reason to take the idea seriously. It completes a revolution that began when we first dared to look up and realize the stars were not lights hung for our benefit, but suns in their own right. That same courageous humility now asks us to consider that our entire cosmos might be one light among many in a greater firmament of realities. To embrace this possibility is not to diminish our story, but to place it within the grandest narrative of all, a story where existence, in its boundless creativity, refuses to be confined to a single stage. We have walked through a landscape of clues from the quantum realm to the cosmic horizon, 30 distinct lines of inquiry, each born from a different mystery, have all pointed toward the same breathtaking vista. This is not a case of one clever idea explaining everything. It is a convergence, a chorus of voices from the frontiers of cosmology, quantum physics, mathematics, and philosophy, all singing in harmony about a reality far grander than a single universe. The fine-tuning of physical constants, the paradox of quantum measurement, the puzzle of our low entropy beginning, the eerie silence of the cosmos, these are not separate problems. They are pieces of a single, magnificent puzzle. The multiverse framework offers a place for each piece to fit, addressing them not with 30 different answers, but with one profound shift in perspective. Our cosmos is not a solitary stage, but one performance in an endless festival of existence, where every possible story is being told. While a single, definitive observation, like a cosmic bruise from a bubble collision, remains just beyond our current grasp, we must weigh the evidence we have. The cumulative case is built on theoretical elegance, the remarkable explanatory power to solve multiple deep puzzles at once, and even predictive successes like forecasting the range of dark energy. It provides a coherent narrative where our universe's apparent specialness is revealed as a statistical necessity, and the weirdest rules of quantum mechanics become a natural feature of a branching reality. This is more than just another scientific hypothesis. It is an invitation to a fundamental rethink of what reality is. It challenges the very notion of a lone, self-contained cosmos and replaces it with a vision of boundless creativity, a reality so abundant that it refuses to leave any possibility unfulfilled. In this view, we are not accidental visitors in a cold, empty void. We are participants in a celebration of existence so vast and fertile that every note in the symphony of possibility finds its expression somewhere. The question is no longer whether such a reality could exist, but whether we are ready to embrace the profound and beautiful humility it requires of us. This tapestry of ideas reveals a cosmos of breathtaking generosity. We have traced the threads from the first inflationary bubbles to the endless quantum branches, weaving together 30 distinct strands of evidence that point toward a reality far grander than our own. Each reason, from the fine-tuning of constants to the eerie silence of the stars, finds a natural home within this expansive vision. It is not merely a speculative idea, but humanity's boldest and most humble attempt to map the ultimate architecture of existence. As physicist Brian Greene once reflected, the multiverse may indeed be the next great revolution in our cosmic perspective. It asks us to exchange a comforting, singular story for a magnificent and humbling truth, that our universe is likely one note in an infinite symphony. So we leave you with a question to ponder. Has this journey shifted your own view of what is real? Let us know in the comments which reason resonated most deeply with you. If exploring these profound mysteries of space and reality sparked your curiosity, subscribe for more voyages to the edge of understanding. The search continues with wonder as our guide in this universe and perhaps in countless others.